Finally, we will put up a note on the direction of acceleration and velocity. So the equations that we have derived till now are based on this configuration where the crank rotates clockwise and the displacement x of the piston is from IDC. So based on this, so this is a positive direction for displacement. Okay, and this is negative direction for displacement and velocity and acceleration. So this is the positive direction towards crank pin is positive and away from crank pin is negative. So we have followed this convention. This is a positive angle theta. This is a positive angle theta in our derivation, and the crank rotates clockwise. In many gate questions, you will find that a simple thing will be changed. Like the configuration will look almost same. The x is from the inner dead center, but the crank rotates anti-clockwise. So in that case, you have to replace all equations with negative omega in place of positive omega. So this thing you have to keep in mind. This configuration you just have to memorize, because if the question is asked like this, let's say we will take one more example. So a question is asked with this figure. This is A, this is O, this is B. Length of AB is given as 16 centimeter. OA is given 6 centimeter, that is radius of the crank. So L is 16, R is 6, and the theta is given as 45 degree. So in this case, omega, the crank velocity, is derived from number of revolutions. 1000 rpm is given by 60. So 1000 rpm anti-clockwise. And the question asked is find acceleration. There are 4 choices given. So acceleration, so is it towards O or away from O? So 4 choices will be given. One will have one numerical value, say 5 towards O. Second option will be 5 away from O, etc. So 6 away towards O, third option. Fourth option, 6 away from O. So like that 4 choices will be given. So you need to find out the direction. In that case, you remember our original derivation was for the clockwise crank rotation. You put the values L, R, theta in the equation for the acceleration that you already know. Acceleration is omega square R cos theta plus cos 2 theta by n. And when you are putting theta like this, so here you get the absolute value. And in our original case, the theta was in direction of a crank movement, so theta was taken as positive. In this case, theta will be taken as negative. So you will substitute minus 45 degree in this expression and get the answer. So I am leaving the numerical calculation part here. That is pretty much straightforward. You have to just put the value of n, theta, and omega in this expression and get the expression. For the direction, if the acceleration is negative, it is away from crank pin. It is positive, it is towards the crank pin. Like that, you can get the correct answer. Now we move on to the next topic in the dynamic analysis of slider crank mechanism, that is engine force analysis, which is force analysis of slider crank. So the slider crank mechanism is used in an IC engine. So a real IC engine, the reciprocating engine, which is subjected to various forces, the forces such as reciprocating masses of connecting rod, crank, piston. So the reciprocating nature of the motion of this load lead to inertial forces, because the acceleration is continuously change the velocity in required force to accelerate the component. So reciprocating masses lead to inertial forces. Then weight of reciprocating components, the center of gravity is changing at every time instance. So the weight will act in different direction at different time instance. Direction change with time. So the load coming on the crank or the piston will vary with time. And then force by gas in cylinder on piston. So in IC engine, the combustion leads to high pressure on the piston. In a compressor, the piston is transferring energy to the gas, but in both the cases, there are forces on the piston. These are various forces. In present section, we are analyzing the forces, neglecting the effect of the weight and inertia of connecting rod. So we will do the force analysis for the piston. Basically, we will consider the mass of the piston, the inertia of the piston, weight, and forces from cylinder, and how this force transfer of force at piston to the crank pin and crank and connecting rod. So we will see transmission of forces from piston to connecting rod and crank, but we will neglect the effect of weight and inertia of the connecting rod. So we will draw the diagram for this analysis, which is what. So this is our crank. The crank radius is R. The length of the piston is L. This triangle is B, A, O, and draw a perpendicular here. Point coming here is P. This is theta, the angle of the crankshaft, and this is beta, the angle of the connecting rod with respect to horizontal. Now we will introduce forces also in the system. So the force due to the pressure of the gas is termed as Fp. The normal force on the piston by liner is termed as Fn, the normal force. These are two additional forces. In addition to these two, there will be the reciprocating inertial force. If you keep on changing direction, the inertial force will term as Fi. So we will find out these forces one by one. So for calculating Fp, you take the geometry of the piston. Piston looks like this. So there is a gland ceiling here. This is a piston rod. So this side is 1, this side is 2. So let's say this side's area is A1, area on gas cylinder side, and A2 is area on, this is a piston area, that is piston area minus this is the area of the piston rod on rod side. So this is equal to piston area minus rod area, and let's say P1 is pressure on gas side and P2 on pressure on rod side. Then the FP, the force due to gas pressure will be P1 A1 minus P2 A2. P2 multiplied by A2 simply. What is the normal force between between piston and liner? That will be given. That we cannot determine in this analysis. It will be depending on pressure of the piston rings, and it will be normally a given quantity. The force, the inertial force Fi, inertial force, that you know, force is equal to mass into acceleration. So we know the mass of the piston m, let's suppose mp, and acceleration of piston we know that it is omega square r cos theta plus cos 2 theta by n from our earlier derivation. So the inertial force will be mp omega square r cos theta cos 2 theta by n. This we can determine from angle theta. It will be changing direction with time. So it's a reciprocating mass inertial force. How it is changing direction we'll see in the next slide. So regarding direction of the inertial force, the inertial force basically depends on cosine of theta. So if you recall the diagram of cosine, this is 90 degree, this is 0 degree. From 0 to 90 degree cosine is basically positive. And that is why the 2 theta is also equal to 90. That means theta is equal to 45. So till theta is equal to 45, till theta less than 45, theta going up to 45, is both quantities will be positive. So Fi will be positive. So our original convention for derivation was that the displacement x is from the IDC in the dead center. So x is positive in this direction towards crank center. X is positive towards crank center. So if you get positive acceleration, that means acceleration is towards crank center. Obviously for the crank rotating in a clockwise fashion. If the crank is rotating in an anti-clockwise fashion, all the things will be reversed. So omega is clockwise for all this purpose. So for that we get till up to 45, the acceleration is positive, the acceleration will be towards the crank center. After theta greater than 45 also, up to some extent the cos theta will remain positive, but the cos 2 theta will start to become negative. So at the point when cos 2 theta is equal plus cos 2 theta is equal to 0, up to that point the acceleration will be positive. So that value we saw in our earlier example, the numerical example, it is somewhere near 78 degrees. So till 78 degrees from the inner dead center, till 78 degrees, acceleration is positive, that means towards the crank center. After that it will reverse the direction and it will become away from crank center. So the exact angle at which the direction reversal takes place, the piston starts to accelerate away from the crank center, can be determined from this equation cos theta plus cos 2 theta by n. For n is equal to 5, we got this value in our earlier numerical example. For different n, it will be different. So if it is asked when the direction reversal takes place or when the acceleration is 0, you can use this identity. However, for our present purpose, we want to know that what is the nature of acceleration when it starts from IDC or ODC. So starting from IDC, we know for sure that acceleration is towards the crank center. So that means the connecting rod diagram, just quickly draw it here. So the acceleration is towards the crank center when you are starting from IDC. Now the inertial force, as we know, is opposite the acceleration. So inertial force tries to stop the acceleration. If the body is naturally getting accelerated in this direction, the inertial force will be applied in the opposite direction. Acceleration is in this direction towards the crank pin. That time the force will be away in the opposite direction of the acceleration, that is away from the crank center. So first half of stroke, nearly first half of stroke, that will depend on n, where the acceleration reversal takes place. Approximate we will put here. The Fi inertial force is away from the crank center, and at the later half, when it reaches the outer dead center and starts to come back, so start of return stroke towards that period, Fi is towards crank center. Now why we are interested in this one? Because we want to calculate the term known as piston effective driving force, net or effective force applied on piston. So this is made up of two components primarily, that is Fp, the gas pressure in the cylinder, and Fi, the inertial force. So the gas pressure from this diagram, the Fp is always in a direction towards the crank center, because normally the area on the piston side will be higher than the area on the rod side. A1 will be greater than A2 and P1 will also be greater than P2. So pressure and area both are normally greater in the piston side than the rod side, and this Fp is P1 A1 minus P2 A2. So over most of the cycle of IC engine or reciprocating engine, the pressures are positive, and the P2 is the ambient pressure, that is zero pressure we take, and P1 is above than P2. So reciprocating compressor also. So normally Fp will be positive always, so it will be always towards the crank center. Now for the Fi, the inertial force, we know that Fi is in direction opposite to the acceleration. So in first half of stroke, the acceleration is towards crank, hence the inertial force is away from crank. and hence the inertial force acts in a direction opposite to the pressure force. So Fi is in opposite direction to the Fp. So hence Fi reduces the force applied by piston on the connecting rod. So that this is called the net piston effort, which is the topic of present discussion. So this quantity is reduced during the first half of the stroke. In the later half of the stroke toward the outer dead center, this thing gets reversed. So Fi is also towards the crank pin and Fp is also towards the crank pin. So the inertial force augments the pressure force, and net force on connecting rod is increased. By the same amount. So the magnitude is same, but the direction changes with the crank angle, and this towards the inner dead center it opposes the pressure force from gas, and towards the outer dead center it augments or aids in the same direction as the gas pressure force. So what is the net force on the piston? Net force is equal to Fp, the pressure force, I, and then you can take the additional thing, that is frictional force. So frictional force is, if you know the normal force on the between the piston and the liner, that Fn, during the start of the discussion we said, then coefficient of friction multiplied by Fn will be the friction force. So plus mu Fn, the normal force between piston and liner. And then finally, if the cylinder is vertical, the gravity force plus Fg, gravity force, which is normally equal to mg, mass of the piston and gravity. So the direction you can determine based on the alignment of the engine, vertical or horizontal. Based on that, this force will be determined. So this net force we will be using for our next step for determining the thrust on the connecting rod. So the second calculation in engine thrust analysis is the force along the connecting rod. So if you draw the slider crank diagram, this is the connecting rod AB, this is the piston, the liner. So this is the connecting rod. The thrust in the connecting rod is what we want to determine in present study. So Fc is the thrust in the connecting rod, and the connecting rod makes an angle beta with respect to the horizontal axis, and we know the net force on the piston. So F is the net force, net piston driving force, that is the combination of the gas force Fp plus inertial force Fi plus frictional force Ff plus gravitational force Fg. So F is known, the net resultant of all these forces. Now if you just equate the forces along a direction, along the horizontal direction, you equate the horizontal component of forces. So the component of Fc along horizontal axis, so Fc at the piston, if you see the balance of forces, Fc is determined applied like this at angle beta, and F is applied in the horizontal direction. So the component of Fc in horizontal direction is Fc cos beta. So that's why we have, by equating the forces, Fc cos beta is equal to F. So this is how we can determine Fc, which will be equal to F divided by cos beta. So if you know the net force, net piston driving force, you can calculate the force along the connecting rod. by dividing it by cos beta. The third step in the piston in the dynamic engine force analysis is thrust on sides of cylinder. So this is an interesting thing to observe because it is not a natural force involved on the piston, but it is generated due to a component of force along the connecting rod. So as you see from this diagram that FC is at angle beta to the horizontal and F is along the horizontal. So if a component of FC cos theta is equal to F here, then there should be a component of FC that is acting normal to the piston. So that component is FC sine beta. So this is the thrust on the side of the cylinder, side walls of the cylinder. So due to the piston. So this is the piston, this is the cylinder. This is normal force between the piston and the cylinder, that is equal to Fn is equal to Fc sine beta. If you substitute a value for Fc, that is F by cos beta sine beta, then Fn becomes F tan beta. So this is interesting not because the Fc cos beta is equal to F, and since cos beta has a maximum value of 1, it will always be less than 1. So Fc is greater than F. F is just a component of Fc. But the main cause for all the thrust in the connecting rod is F. But because of F, a force is generated in the connecting rod which is greater than F itself. And a component of that force which is generated in the connecting rod acts normal to the piston also, and it is Fm. That can be calculated by F tan beta. The fourth quantity of interest in this section is the crank effort. So the crank effort is nothing but the force exerted on the crank pin due to piston net force. So this is a quantity of paramount interest because the crank effort will give us the turning moment on the crankshaft. So this is normally the output or input torque. So for IC engine it will be output, for compressor it will be input torque, and this thing will be a function of time. So as F is changing, the crank effort also changes. So what is the relation between the crank effort and F, the net piston force? For that we will draw the diagram again. This is the crank circle, this is the crank, here it is pivoted, and this is the connecting rod connected to the piston liner. So if you draw the trigonometric triangles, here the angle is beta, here the angle is theta. So the turning moment will be a force perpendicular to the crank. So if you that's how if you multiply that force, let's say we term it Ft represent. So Ft into R will be the torque, output torque. Okay. We are interested in Ft. Here F is applied on the piston. Fc is the compressive thrust in the connecting rod, and Ft comes here. So how the transmission takes place here, that's for that you have to draw the balance of forces along component in this direction. For that what we do is that we extrapolate this triangle and we will draw a perpendicular from the crank to this triangle, from the crank center to this triangle. Okay, now in this triangle, we know this angle. This line, the connecting rod, is extrapolated to a point, say D. This is A, this is B, this is O. So AD is extrapolated to the angle OAD is known. That is beta. This is the sum of the interior angle. You know that the exterior angle is sum of the interior and opposite interior angle from simple trigonometry. So this becomes beta plus theta. Beta and theta are the opposite interior angle, and this is the angle OAD. Okay. So you know that now the FC is acting along the line AD. So the if FC is acting along AD and we know the perpendicular from O is drawn to the AD, then the distance, let's say it is some quantity P. So the distance P, which is OP multiplied by FC, will also be the torque, the turning moment. Because this force is the torque on the system will be same whether you take FC into OP or you take FT into R.